Okay, and I'm going to go back quite a bit, maybe just to remind you what some of these important things are. The really important thing is that well, the definition of what it means to be differentiable, what it means for a complex function to be differentiable. And it means that the limit of the function, well, here, let me just say it again as a reminder that f of z minus f of z0 over z minus z0 should go to f prime of z0 independently of how z goes to z0. So it might take that route. It might do this. It might go around like that. And or it might, I think I've now used all the simply available colors. It might take that black route. So that's what differentiable at a point means. If a function is differentiable inside a disk, it's analytic in the disk. And if a function's analytic, then an integral, a loop integral, but as long as the loop and everything inside the loop lies inside the region where f is analytic, then the loop integral vanishes. And we also showed Cauchy's integral formula, which is that the loop integral of the function, oh, that's a mistake. There's a mistake there. Let me, the great things about this iPad is that one can correct one's mistakes. So there it is that f of z over z minus 0 dz integrated around the circle, in a circle around, oh, well, it can be any loop around z0 is 2 pi I times f of z0. We also learned Cauchy learned of criteria that tell us whether, let me raise this table. We also learned that how to tell if a function f of xy of two real variables is analytic. We write its real and imaginary parts like this, and it's analytic if the Cauchy-Riemann conditions are satisfied, which are that the x derivative of u is the y derivative of v, and the y derivative of u is the x derivative minus the x derivative of v. And this subscript notation is that this is equal to minus partial v partial x, and this is partial u partial y. So that's what the subscripts mean. These Cauchy-Riemann conditions we saw have an immediate consequence, namely that the real part of an analytic function is harmonic, and the imaginary part is also harmonic. And harmonic means that the second x derivative plus the second y derivative vanishes. And the reason why that is true is that, for example, uxx, well, remember by the Cauchy-Riemann conditions, ux is vy, so this is vyx, which is also vxy. But on the other hand, the Cauchy-Riemann conditions is that vx is minus uy. So this is equal to minus uyy. So that tells us that uxx plus uyy equals 0. And a similar thing tells us that vxx plus vyy equals 0. So these, so u and v are harmonic. So let me go back to where in the book we were talking about these things. Yes, harmonic functions. And so basically, if they're harmonic, what do we have as a consequence? Well, a harmonic function cannot have a minimum or a maximum. It can have a saddle point, which is to say that if you go up here, it's increasing, and then when you go down the other side, it's decreasing. So that looks like a maximum, but on the other hand, if you come down this way, and you then find that what you've got here is a minimum in the perpendicular direction. So that's what a harmonic function looks like. It has saddle points, but it doesn't have maxima or minima. You remember for static fields, the electric field is, here, let me switch maybe to black. The electric field is minus the gradient of some potential, called the scalar potential. And this is for static fields in, well, for static fields, that's also always true. Gauss's law is that the divergence of E, which is minus the divergence of the gradient of phi, is equal to the charge density over the electric constant. So in empty space, del dot E, which is minus Laplacian of phi, is actually just 0. So that means that phi xx plus phi yy plus phi z equals 0 in empty space static fields. And what that means is that an electric field or an electrostatic potential has no minimum, no minimum, no maximum. And in particular, that means that with an electrostatic field, you can't, I mean, you'd think with an electric field, you could confine an electric charge. You could certainly move an electric charge, but you'd think you could move it into a particular place and keep it there. Well, you can't, because the scalar potential is harmonic. Harmonic means the sum of the second derivatives vanishes, and that term harmonic applies to whether you have you're in 3 dimensions or 4 dimensions or 2 dimensions, I guess even 1 dimension. Anyhow, a harmonic function can't have a minimum, so the electrostatic potential has no minimum, and so you can't confine a charged particle with just electric fields, and that's why in these experiments that where people do confine atoms or charges in a particular place, they have to use time-dependent fields and often use lasers as well, and electric fields, magnetic fields, and so forth. Obviously, I'm not an expert on that, so I can't give you the details. What is true, though, is that if you imagine that you have an electrostatic field that is independent of one dimension, independent of translations in one direction. So, for example, it's independent of z, it just depends on x and y. Then you can take the real part of that. You might have u would satisfy uxx plus uyy equals 0. And this could be the electrostatic potential of an actual physical electric field that is independent of Z. And so that's something that's sometimes applied, and it's, if you have this situation, you have infinitely many exact solutions of that kind of problem, because there are infinitely many analytic functions. The real and imaginary parts of an analytic function turn out to have gradients that are perpendicular. So in other words, the derivatives of x, of u, the real part, dotted into the derivatives of the imaginary part give you this expression here, but by inasmuch as ux is equal to vy and uy is minus vx, they add up to 0. And so the gradient, in other words, if you have an analytic function, then let us suppose that that is constant u. And now if we switch, constant v is going to be instead something like this, or something like that, or something like that. So the fields of constant u, the lines of constant u and the lines of constant v are going to be mutually perpendicular. It looks like that. And that's because of this expression here. I think I'm going to skip these examples. Let's go to Taylor series. And this is the point of this. We've already done Taylor series, but the point here is that if you have an analytic function, then you automatically have a convergent Taylor series. And in fact, we'll find out that it converges. Well, we'll find out how it converges. So first, we're going to use Cauchy's integral formula to give us f of z as an integral, z prime integral going around z. And then what we're going to do now is we're going to have, we're going to have a particular point. So let me get plenty of space. Oh my goodness, what was that? We're going to, so I want to have a point here, z0, and then let me see what the diagram, yeah, all right. So we're going to have we can just have a curve around this, and I'm going to make a circle here. And so this can be a contour C, and so we can write f of z in this way. And now what I've done is I've gotten ahead of myself. Z is some arbitrary point here. Z0 is the center of the circle. And so what we're going to do is we're going to add and subtract Z0, and then we're going to factor that denominator like this. So we write z prime minus z is z prime minus z0 minus z0. And then we write this as z prime minus z0 times 1 minus that. It looks like that. Okay, so what is next? Well, the point is that we can then write this factor here, well, let's see, maybe I should have written a little more of it here. In other words, what we've got now is that f of z is equal to 1 over 2 pi I integral, and we're still integrating along C, and we have f of z prime over, and when we factor it out, we have z prime minus z0 times 1 minus z0 over z prime minus z0. And now the point here is that z is closer to z0 than any point on the curve is. So in other words, this distance is less than this distance. And this would be obvious if I had drawn this as a perfect circle, but I didn't. But it's sort of obvious here that z is closer to z0 than z prime. Z prime is along here, and I forgot a dz prime. Okay. So now what do we do? Well, what we do is we expand this denominator because it's of the form 1 over 1 minus epsilon. Of course, that's a sum of epsilon to the n from n equals 1 to infinity. That's one of the formulas in the chapter on infinite series that is worth remembering. Now I see that I've not written this super clearly, so let me write this as a 0 there. So we do that sum, and again, this thing is epsilon. Well, this series converges absolutely and uniformly inside a circle as long as epsilon is less than 1. And here, this epsilon is just the ratio of this distance here, the black distance to the yellow distance, basically. And so we can then do that sum, and we're going to now that sum converges absolutely and uniformly inside the circle, and so we can pull the z minus z0 to the n outside and leave the denominator inside, and so we get this nice expression here. And but now you remember Cauchy's integral formula. And Cauchy's integral formula is that the nth derivative at z0 is equal to n factorial over 2 pi I times this integral of f of z prime dz prime over z prime minus z0 to the power n plus 1. And just to make sure that I've got the this correct, I'm just checking on the right-hand side here, and indeed I did remember it exactly correctly. So this thing here is the nth derivative of f at z0 divided by n factorial. And so we can rewrite this thing as, in other words, this sum is, let me switch maybe to blue here. F of z then is, as we wrote it up there, it's a sum n equals 0 to infinity of z minus z0 to the n. And then what's left there is the nth derivative at z0 divided by n factorial. And so that's this expression here. And it converges as long as the point z is inside a circle centered at z0 that lies within a simply connected region in which f is analytic. So In other words, what we need, of course, is analyticity over this entire region. We need analyticity there. Okay. Now, of course, this is quite a useful thing that we have. Well, of course, you might have guessed that there would be a complex generalization of Taylor's theorem, or of Taylor's series, which are normally on the real axis. This is a generalization, and it's a very useful generalization. And I see here once again, I've written something that isn't super clear, so let me write that as an N. Okay. The next topic is Liouville's theorem, one of Liouville's theorem. He had many theorems. So let's suppose that f of z is everywhere analytic, so it's an entire function. And now we're going to make an assumption that will turn out to be nuts. In other words, we're going to assume that f is bounded outside some disk. And, oh, wait a minute, did I skipped something? Yes, I skipped Cauchy's inequality, goodness. So we want to do Cauchy's inequality first. So suppose f of z is analytic in a region that includes a disk. So we've got a disk here of radius r. And we're saying that f of z is bounded that it's analytic in a region that includes this disk, and that f of z is bounded by f of z is less than or equal to m on the circle that is perimeter. So on this circle, in other words, on this circle, this inequality holds. So then what we do is we use, and we imagine this whole thing is analytic in a region. So we have a region of analyticity that includes all of this. And so what we can say is that we can use Cauchy's integral formula to compute the derivative at the center. Here I've taken the center to be 0. So the nth derivative at the center of the circle, which I'm taking to be the center of the complex plane for simplicity, is the integral of f of z dz integrated around the perimeter. And in other words, I'm using exactly this formula here with z0 equal to 0. And now the absolute value of that then is bounded by this. We just replace everything by absolute values and cancel the I, place the I by 1. But now we're saying that f is bounded on this perimeter by capital M. So we can pull out the capital M and get rid of f of z. And now we just have d theta, which is 2 pi when integrated over r to the n. So this is a bound on the nth derivative. And now if we go to the Taylor series for the function, what we do is we sum, and it's going to be a sum z minus z0 to the n fn of z0, and that fn of z0, the n factorial is going to cancel there, and we're going to have r to the n here. And now this converges absolutely and uniformly for z minus z0 less than r. And so I guess what we're saying here is that the inequality is that the nth derivative is bounded in this way. And of course, one of the things that means is that as you send Rn to infinity, this means that these derivatives, in fact, this holds for arbitrary n, so all the derivatives have to vanish. I'm just wondering if I left something out here. Well, apparently I applied it here. So let's now suppose that we have a function that's analytic everywhere, and it's bounded outside on a circle and outside that circle. So then if we apply Cauchy's inequality, we get that Fn of 0 is less than this. We send r to infinity, and we conclude that the nth derivative at 0 has to be 0 under these conditions. So every derivative at 0 is 0, but then that means that the Taylor series is a constant because all these derivatives vanish except the 0th derivative, which is the function at 0. So the result here is that every bounded entire function is a constant, and that's Liouville's theorem. So it's an application of Cauchy's inequality. So maybe to just repeat the logic here for a moment, you use Cauchy's integral formula to show that that the nth derivative at 0 is less than or equal to the bound of f on the circle divided by the nth power of the radius of the circle, if we have analyticity and boundedness. And so now if we're saying that a function's analytic and bounded outside, and for all z bigger than a certain circle, then we get this condition for arbitrary r. We send r to infinity and we get that the function is the derivative, the nth derivative is 0 except for the 0th derivative. So the conclusion is that every entire function that is everywhere bounded is a constant, or to put it differently, every function that's analytic everywhere and bounded everywhere must be a constant. And one theorem of complex variable theory actually is that if you have an analytic a function that's analytic everywhere and isn't a constant, then it can't be bounded. And in fact, as you send z to infinity in some direction, it's bound to diverge. Okay. So now we can prove the fundamental theorem of algebra, which is something that I advertised a couple of weeks ago. And it was Gauss who applied Liouville's theorem to a function 1 over an arbitrary polynomial. The c's are just constants. And of course, it's a polynomial in a complex variable z. Well, suppose that the polynomial had no root anywhere in the complex plane. Then f would be, then the denominator would never be 0, and it's just an inverse of a polynomial, so it would be analytic everywhere. And moreover, if you let the absolute value of z be big, then the absolute value of f would be small, and you could say, in fact, that it was bounded for z outside some disk or outside some circle. And so it's bounded by m. But the conclusion of that by Liouville's theorem is that f would have to be a constant. And on the other hand, f is obviously not a constant because it's an inverse of an nth order polynomial. The conclusion is that p has a root. So if Pn has a root, what we do is we rewrite it as z minus z1, where that's the root, and another polynomial of a lower degree, a lower order. And then we repeat the argument, and the result is that we find that every polynomial has n roots in the complex plane. Now, they need not be all different. In fact, one possible polynomial is Pn of z is equal to z to the n. So that has n roots, but they're all 0, all z equals 0. So z equals 0 is a a root of order. My God, where did that come from? Can I get rid of it? I don't know. Oh boy, oh, there, it's this damn thing. All right, hold on. Maybe I can get rid of it there. Oh, okay, it's gone. Okay, it's a root of order n, or root of degree n. Names that are assigned to various things are sometimes escape me. Anyway, so every polynomial in the complex plane, if it's a polynomial of order n, then it has n roots. And sometimes they're all the same. So, well, rarely are they all the same. Typically, they're all different, but they could be all the same. Okay, the next topic is a different way of writing. It's sort of a generalization of Taylor series. So we're going to be considering a function f of z that's analytic in what's called an annulus. And so here I'm going to try to draw this somewhat. Actually, I've got two circles here, so let me see if I can draw it this way. Here I'm going to go around like this. Oh, then the tricky thing is going to be putting the second circle in the right place. So I don't know if I'm going to get this right. So let me just then go around here. So I've got two circles, but they're probably not. No, they're not. So as I said, now I've got water on the iPad that I have to get rid of. Okay, so let's imagine that these two are at the same place, and so they have the same center, and I'm going to call that center Z0, and then I'm going to imagine that we integrate this way along C1, and then we integrate this way along C2, and I'm going to imagine that there's some point Z here, and my dog is in there. That he wants. Anyway, but what we're going to do is we're going to join these two contours by going over here and imagining that we can go in like this and then out again like that. And we're going to let those two contours approach each other so that the integrals along one cancels the integral along the other. And so what can we say at this point? Well, the point Z is inside the, if we imagine, let me just move around like this. Okay, so if we imagine one big contour, namely one that goes around this way, down, around, across here, up and around like that, and then comes back to the original point, wherever that was. I've now forgotten where that was. How can I get rid of this thing? Then what we've got is a closed contour that is counterclockwise and encircles Z and lies in the region of analyticity. What I forgot to say is that there can be singularities in here. So I'm going to put some singularities in here, and the singularities are going to be these black things. So these are singularities, and might be some out here also. So that's basically the idea of the situation here. So we've got a situation where you've got singularities, but we have a region of analyticity. That is to say, this region here. Wait a minute, I wanted to make that a brush. All right, so let me get rid of this. So this region here is a region of analyticity. And then, and it's an annulus, which is something in between two circles. And so if we do this funny integral along this contour, which now is blue here, and unfortunately over here is green as well as blue, that by Cauchy's integral formula, f of z is given by that. But now what we can do is we let the two blue lines approach each other, and so they cancel. And so we just have two integrals around two circles. And so it's the integral counterclockwise around C1. And now C2 is clockwise, but if I subtract, all right, so all right, I made, well, I'm using things in a sort of complicated way. In other words, if we subtract the counterclockwise integral around C2, so C2 is meant to be counterclockwise, and if we subtract it, then it's this clockwise one here. Anyway, this is what we get for f of z. But now the key point here is that the point z is going to be points z have a certain distance. Well, let me see. We don't want that, do we? We want it to be right in there. So there's a certain distance here of z minus z0. And there's another distance here, this distance. And then there's a third distance, which is, let's do blue, this distance. So there are three different distances here. Now, obviously, the yellow distance is greater than the red distance and less than the blue distance. And that's written in these formulas here. Namely, I'm doing z double prime is on this inner circle. And so it is a red distance from z0. And so c double prime over z minus z0, it's less than the yellow distance. And so in fact, what I could do is I could write this inequality, these inequalities. So z double prime minus z0 is the inner circle. So that is, we have then, whoops, z double prime minus z0. And then I'm going to write, oh, Jesus. I don't know why it always defaults to the wrong thing. And now I'm going to divide by z minus z0, and z minus z0 is yellow. And so in absolute value, and that's less, Jesus Christ. That's, well, I want to do this in less than 1. In fact, I can make it like that. And what we also have is that z minus z0, which again is yellow, and that's less than z prime minus z0, where Z prime is on the outer circle, and so that's blue. And that's also less than 1. So that's the picture in colors. We have these two inequalities. And then what we can do is something very similar to what we did for the Taylor series. In other words, we add and subtract Z0, we factor, we turn both of them into Taylor series. And the Taylor series then are, there's a curious thing that happens. This first Taylor series is Z minus Z0 over Z prime minus Z0. So that's this inequality. The second one has Z double prime minus Z0 over Z minus Z0. That's this inequality. And both of them then are less than 1. And so we can call them epsilon if we want. And then apply that formula that I've said many times is so important. And we can then sum this as, here, if I move this out of the way, it's sum n equals 0 to infinity. Epsilon to the n is 1 over 1 minus epsilon. And so here we write this is 1 minus epsilon, 1 minus a different epsilon. And each one then becomes a sum, and those are these two sums. And then what we can do is we can do something that, frankly, every time I do it, I get a little bit confused. What we're going to do is we're going to set m here is this integer variable. It's going from 0 to infinity. We're going to set m equal to minus n minus 1, or equivalently, we're going to set n equal to minus m minus 1. And in other words, so let me switch maybe to green. N equal to minus m minus 1 in this sum, or rather m equal to minus n minus 1. Sorry for this confusion. Or equivalently, m plus 1 equal to minus n. And so this becomes z minus z0 to the nth, which is like here. But now what is n doing? N is going from minus infinity to plus infinity now. So we can rewrite the two of these as one sum. And this is called a, well, in an American accent, it's a Laurent series or Laurent series. In French, it's something closer to a Laurent series. I assume he was French. I don't actually know. And it's often written this way: z minus z0 to the n summed and times some a sub n at z0, because this thing just depends upon z0. And the a sub n of z0 is this integral divided by 2 pi I. Yeah, he must have been French. Pierre is his first name. So when n is equal to minus 1, that's called the residue of the function at z0. Some people make a big deal of residues, but I don't know. I don't think they're all that important. I mean, compared to anything, compared to all the other things. Now, this Laurent series is from minus infinity, n runs from minus infinity to plus infinity. And as I said, just any analytic function can be expressed that way. What is a little different, or let us put it this way, the functions that we normally deal with and the functions that are actually most useful are ones that don't have series that go from minus infinity to plus infinity, but start at some negative L or start at some positive L, but have a finite starting point and then can go all, they frequently go all the way to infinity. And so there's sums from n equal to minus L to infinity of this expression here, where again, the ANs are given by the same integral. And you can find the first coefficient just by taking the limit. Z minus Z0 to the L f of Z gives you the first coefficient. And then you find the second coefficient by subtracting from the Laurent series. You subtract the term that you found, and then you multiply by Z minus Z0 to the L plus L minus 1, and you get the second coefficient and so forth. That's one way of doing it. Now, the next topic is singularities, and the concept is quite simple. A function that's analytic everywhere is entire. Entire functions then have no singularities, but on the other hand, as I said to you earlier, by the theorems that we just went through earlier today, the absolute value of the function f of z has to go to infinity as the real or imaginary part of z goes to infinity. So in other words, if you go out in the complex plane, then in other words, if you have here if f of z is entire, then absolute value of f of z goes to infinity if you go out in the complex plane in some direction. Now, I don't know, depending on what f of z is, you'd have a different direction typically. And some people say, well, z equal to infinity is point at infinity. Point at infinity. I've never liked that expression, but people use it anyway. A function has an isolated singularity at z0 if it's analytic in a small disk around z0, but not analytic at z0. And in particular, a function has a pole if so in particular, an isolated singularity at z0, a typical case of that would be f of z, for example, is equal to 1 over z minus 1. That has a singularity at z equal to 1, and in fact, it has a pole of order 1 at z0 equal to 1. More generally, if you have something like f of z equal to 1 over z minus some z0 to the nth power, this is and of course, this can be f, well, I don't know if I want to call that f, so let me just give this a different number. I'm just going to call this c, some constant over z minus z0 to the nth. We'd say then that this has a pole of order n at z0. And but of course, you could have a function like this, f of z is equal to 1 over z minus 1, z minus 2, z minus 4, say. Well, this would have 3 poles, each of order 1 at z equal to 1, z equal to 2, and z equal to 4. A function that has, notice that these are isolated singularities. So here what we've got is that would be the case here, and we would say that because these singularities are isolated and there are a finite number of them, we say that it is meromorphic. In fact, you could have an infinite number of singularities; it would still be meromorphic. And meromorphic is again a term that's of the same genre as holomorphic, meaning entire. And these both presumably come from Greek roots, holo meaning everywhere and mero meaning somewhere. I don't know. I don't remember those Greek roots. I don't think I ever learned them, actually. Anyway, here's a function that's has a pole of order j at z equal to j. That's a meromorphic function. Okay. An essential singularity is something that's quite amusing and amazing. It's a pole of infinite order. And you might say, how could this be? Well, just write e to the minus 1 over z. That's going to have a pole at, or e to the plus 1 over z, or e to the 3 over z, or e to the 2 over z squared. These all have essential singularities at z equals 0. And what's remarkable is that this man Picard showed that if a function has an essential singularity at w, then inside every disk around w, f takes on every complex number with at most one exception, an infinite number of times. And as an example, e to the 1 over z, well, this can take any complex number w. What is w? Well, log w is 1 over z. So what do I want to say? Yes, so z is equal to 1 over log w. So give me any complex number w, take its logarithm and its inverse, and that's a value of z that will equal such that e to the 1 over z will be w. And of course, when does this not work? Well, it doesn't work if w is 0, because the log of 0 is not finite. And so arbitrarily close to z equals 0, e to the 1 over z takes on the value w an infinite number of times. And you might say, well, why is there an infinite number of times? Well, the different values of z is here. Let me just get rid of that. We can say Zn is 1 over the ordinary log w plus 2 pi plus 2 pi n. How do I want to say this? Log of w, log of right. If I change 1 over z, if I add 2 pi n I to 1 over z, there's not going to be any change. And so this thing would be like that. And so this is what, so you can let n equal 0, 1, 2, 3. As n goes to infinity, the zn's get closer and closer to the origin, and you still get the same w. So that's how that works in that particular case. It's hyper weird, I would say. Here's a meromorphic function with 2 poles at z equals 0, z equals minus 1. We can express that as a Laurent series about z equals 0, for example. for z less than 1. And why absolute value of z less than 1? Well, because when z gets to 1, you're going to hit the pole at -1. The coefficient a sub n is this integral. The contour is, in this particular case, so let me draw maybe a green line. And what we're talking about then is an integral which a circle of radius less than unity, so r equals 1 is out here. And we're integrating along this green circle, and the coefficients then are given by this according to the formula we just derived. And you do the integrals, well, it's 1 over z to the n plus 2 z plus 1, and these turn out to be pretty simple to do. And so this is the Laurent series. It starts at z at n equals -1, and because this thing is meromorphic with only simple poles. I'm going to skip the argument principle. You can read it if you want, and we'll focus on something that's more important, namely analytic continuation. And the basic idea here is that, so let me start something new here. Right? So the basic idea is that if you have a function that's analytic, so f of z is analytic here in this region, which I can then, I guess, switch to. In this region, we're going to say that it's analytic. Well, what's often true is that what you can do is you can imagine doing a Taylor series about some point that's near the edge. And if this red line here, if this red line is really the boundary of analyticity, then you couldn't, then the biggest circle you could do is this for doing a Taylor series around that point, that black point. But typically, that would mean that you picked a really crazy point. But if you pick some other point, just keeps giving me the wrong thing. So we pick another point here. Now we do a series. And this one, if we're lucky, it will be it'll converge and define an analytic function in a larger region. And so what we can say then is that this function f of z is actually analytic in a larger region. In other words, in this particular, it just keeps shifting and so annoying. So in other words, in this region here, this blue region, we can say f of z is this sum z minus, and I'll use black for that z0. And so this thing will now extend the region of analyticity. And so now we'll have a broader region of analyticity, and we'll be able to get out to here. And so that's basically what it is. Now, a really nice example of that is the gamma function. So let's look at the gamma function. Initially, we define the gamma function for the right half plane. In other words, we say, okay, we're going to define, oh God, we're going to define gamma of z in this region to the right. In other words, we can say it'll be this region here to the right and throughout the right half plane. Well, and it's defined in this way, and it's analytic then for real z greater than 0. But we saw before that the gamma of z plus 1 is z gamma of z. And so we can say that gamma of z, of course, is 1 over z gamma of z plus 1. So now we could define gamma of, say, minus 1/2, or we could extend its analyticity. We could extend its analyticity, first of all, back to real z equal to -1 by using this expression, because if z is, say, -3/4, this is gamma of 1/4, and that's well defined and it's analytic there. So then we re-express it as 1 over z plus 1 gamma of z plus 2. Well, then we've gone as far here as real z equal to -2 and so forth. And then eventually we go to -3 and so forth. And the upshot is that the gamma function then is defined throughout the whole complex plane, except for singularities, and the singularities are 0, -1, -2, -3. But apart from 0 and the negative integers, the function gamma of z is analytic, and we can think of this as a very simple way of analytically continuing from the right half plane back to the whole complex plane except for the non-negative integers. And as I said, Weierstrass's formula is one way of expressing that. What's sometimes useful is this expression for Riemann's zeta function. Remember, it's defined this way, and as we learned a few periods ago, it turns out that just in computing the statistical mechanics of a gas of photons or any kind of elementary particle, we'd have a zeta function occurs typically. It turns out the zeta function could be written in this strange way. Well, I don't know why I brought that up, or this. I think we can skip both of them. One thing we can do is we can consider the integral of a function f of z. Suppose that we have an analytic function, and we know that the contour integral is it depends on the endpoints and not upon the path. So you can well, here, let me shift to some other color. If you integrate from z1 to z2 like that inside a region of analyticity, well, you get the same result no matter what contour you take, as long as you go from the same initial point to the same final point and you stay within the region of analyticity. And So we can consider an integral of a function f of z along a counterclockwise contour that encircles n poles. So here's, let me put the poles in here. Maybe one over there. And now what we're going to do is we're going to have a contour that looks like that. That's the initial contour. And we're going to call that as a contour C. And so we can consider this integral of this along this contour C of f of z dz. Well, this is not going to be zero because the although f of z is analytic on the contour and near the contour, it has singularities inside the contour. And so what we can do, though, is we can deform the contour. So we can change it to, staying within the region of analyticity, we can change it to a contour that looks like that. And then we can change it to another contour that just sort of looks like, and the integral along all of these contours is the same. All these integrals are the same. So this is the same thing as the integral along this, let me call this a C prime, f of z dz. And this is the same thing as integral C double prime, f of z dz. So this is C double prime. And eventually we can shrink it so that what we actually have is a tiny integral around this one. And then we go over here, around, and then back, and so forth. And then over here, we actually don't go back immediately. Instead, we go over here, around, and back, and so forth. And so we do these tricks so that we're going around. And I'm going to try to finish this diagram by and so remember what we have here are two lines actually, but they're infinitely close to each other, so they completely cancel. And so what we've got is that this thing is actually equal to a sum over the n poles of the integral ck of size epsilon of f of z dz. But each of these is just the sum k equals 1 to n. This integral is 2 pi I times, each one of these is 2 pi I times the -1 Laurent coefficient at the point zk. So each of these things is this, I guess this is this one here is z1, this is z2, z3, z4, z5, z6, z7. So in this case, we have 7 of these, and n would be 7 in this particular case. And oh God. All right, I've got it back to 0. This is called the residue theorem. So in other words, what we have here is this is the sum k equals 1 to n of 2 pi I times what's called the residue of f at zk. And of course, residue is just the integral of the function around zk. So I think that, in fact, Well, there are all of these equations are this is equal to that is equal to that is equal to that is equal to that is equal to that. So that's how the thing actually works. Might be good to do one example here. Suppose we have a pole of order n. Then if we do a counterclockwise integral around it, we're going to be integrating e to the I epsilon, I epsilon, e to the I theta d theta. But then this thing here is epsilon e to the I theta raised to the nth power. This is a sub n of w. This then gives us a sub minus one. This thing only works for, we get a non-zero result only for n equal to -1. And so we get, what we're getting here is that the integral of f of z around the thing is 2 pi I a sub -1 of w. And so in other words, what this thing looks like is this: you integrate f around the point w and make that just any contour, and we can shrink it to be a tiny contour. Then we write f as its Laurent series, and then the only term that contributes, because you see this integral of z minus w to the nth dz around w in a tiny circle only gives a non-zero result for n equal to -1. And so this gives us 2 pi I a sub -1 of w. And in general, you have to do each of the tiny counterclockwise integrals. But simple poles are special cases. And if w is a simple pole, then the function near w is just a -1 of w over z minus w, and a -1 is just a constant. And so a -1 of w is then the limit of z minus w f of z as you let z go to w, and that's easier to do than actually doing the integral. Here's a function with simple poles, and it turns out to be the zeta function. We are just about out of time. Cauchy's integral formula, which is f of z over z minus w dz equal to 2 pi I f of w, that's an example of the calculus of residues. As I said, I've never been a fan of the calculus of residues. I don't see what the point is of focusing on residues. I mean, it's just one aspect of Cauchy's integral formula, and why emphasize it? The next topic is one of my favorite topics because it's one of the most useful things. And it's what I like to call ghost contours. And so the idea is that sometimes we have an integral here. Let's suppose, first of all, we have an integral of f of z around one contour c. And if there are no singularities out here, we can make it bigger. And then eventually, we can send the contour off to infinity. And if the function well, I just was about to say something that's actually false. If the function, yeah, that's not what I wanted to say. Let me just say that what one can arrange is that, well, for example, this contour integrating this function. See here what I drew were closed contours. You can have an open contour on which the function is arbitrarily, on which the function, as you move it out to infinity, gets arbitrarily small. That's something I call a Gauss contour. And what happens is, if you're integrating along the real axis, you can sometimes add another contour here, and you find out that by sending this contour out to infinity, that the integral along this contour vanishes, and this is called a Gauss contour then. And so then what you can do is you can add the Gauss contour to the integral you have along the real axis. Then you have a closed contour, and then you just pick up whatever singularities are inside. Well, we'll start doing that on Tuesday. It's something quite important. And so this is basically where we're going to stop then. Okay, well, we're out of time. In fact, we're over time. So I'm going to say goodbye. Wish you all a nice weekend. I'm going to stop sharing and hope to see you on Tuesday at 5 o'clock.